This lecture we shall discuss the conservation principle of a mechanical system, and we shall consider that these conservation principles are the outcome of some symmetry of the system. As to be specific, we shall show that if Lagrangian is symmetric about time, that is, if we change the origin of time, then if now the Lagrangian remains unaffected, then we say that time is homogeneous, and we shall show that homogeneity of time indicates the conservation of total energy of the system. That is, homogeneity of time means any time can be considered as our time, zero time or reference time, and if we shift the reference of time, then nothing changes. On the other hand, if we see that if every particle of the system is displaced by the same amount, then if the space is homogeneous, then this translation does not affect anything. If due to this translation the Lagrangian of the system does not undergo any change, then the total momentum of the system remains constant. So the conservation of linear momentum, total linear momentum of the system is an outcome of the homogeneity of space. And finally, if the space is isotropic, that is, if each and every particle of the system be rotated by the same angle, and if the Lagrangian does not undergo any change due to this rotation, then we say the space is isotropic, and we shall show that isotropy of space leads to the conservation of angular momentum vector L. These are the outcome of a more general statement, which is known as Noita Theorem. The Noita Theorem says that for each symmetry of the Lagrangian, there is a conserved quantity. So we shall take up these three one after one. First we consider homogeneity of time. If time is homogeneous, T is homogeneous, then del L del T, so L should not contain time explicitly, and we have this part is 0. This is the implication that Lagrangian does not have any explicit time dependence. We know that Lagrangian L is a function of Qi dot and of time, but we have del L dl dt is equal to summation over I is equal to 1 to n. N is the degree of freedom. This is del L del Qi dot plus del L del Qi dot Qi double dot plus del L del T. If time is homogeneous, this part is 0. So we have, for this part we know that the momentum conjugate to the coordinate Qi is given by del L del Qi dot. So this part is Qi dot. I haven't written this part yet. So this part is Pi Qi double dot. And recall Euler-Lagrange equation. Euler-Lagrange equation is ddt of del L del Qi dot is equal to del L del Qi. This is ddt of Pi is equal to del L del Qi. This is actually Pi dot. So this is Pi dot. So this term can be written as summation over I is equal to 1 to n ddt of Pi Qi dot. So that when we differentiate this, we give this term results, and we can rewrite it as ddt of summation over I is equal to 1 to n pi qi dot. So we write that ddt of summation over I is equal to 1 to n pi qi dot minus L, this summation is over this, is equal to 0. As we shall know, see in Hamiltonian dynamics, this is H, or we get dH dt is equal to 0, which shows that H is equal to a constant. And if we shall also show that for conservative system for which the transformation equation does not contain time explicitly, then H is actually total energy of the system. Let me first tell you that the transformation equation actually is an equation involving generalized coordinates in time. So we get Vi is equal to dRi dt, which is summation over j del Ri del qj dot plus del Ri del d, and j is equal to 1 to n. If the transformation equation does not include time explicitly, then this part is 0. For such transformation, this leads to the case that this is T plus V, total mechanical energy of the system. So, for conservative system for which transformation equation does not involve time, then the total energy is a constant of motion, and this total energy, the conservation of total energy, is an outcome of the fact that homogeneity of space. Now we come to the homogeneity of time. The conservation of total energy is an outcome of the fact that time is homogeneous. If the space is homogeneous, that means that if we shift the origin of our coordinate system, the Lagrangian of the system does not undergo any change. That is to say that if we change Ri, the position vector of the ith particle, to Ri plus delta Ri, and this is equal to Ri plus epsilon. That is, each particle is shifted by the same amount. That is to say, the coordinate system has been shifted. So, if the space is homogeneous, then this Ri and this Ri will resolve the same Lagrangian. That is to say that delta L, which can be written as summation over I is equal to 1 to n number of the particles of the system. This is del L, del Ri, delta Ri, dot delta, sorry, this is del dot delta Ri, because it is the scalar. So we write it as one to n. I have missed one term here. So this is plus del L del Ri dot delta Ri dot. Now recall that delta Ri is equal to epsilon, which is a constant. So this gives you delta Ri dot is equal to 0. So this term drops. And we have del L del Ri dot delta Ri, this is equal to del L del Ri dot epsilon. As we have shown here that del L del Qj is actually Pj dot. So this term, this del L del I is actually summation over I. This is equal to 1 to n, the number of particles of the system, not over the degrees of freedom. This is Pi dot epsilon, which we can write epsilon dot ddt of summation over Pi. In writing this equation, we have used that as Pi dot is equal to del L del Ri, del L del Ri. So we define this as epsilon dot times dp dt, where the capital P is the vector sum of the individual linear momentum of the system. Since this part is 0, since delta L is equal to 0, this is an outcome of the homogeneity of space. That is, if we change this, the corresponding there will be no corresponding change in the Lagrangian. This is the symmetry, and since epsilon is arbitrary, which shows that dp dt is equal to 0, which shows that p is equal to summation over I, small pi is equal to a constant vector. So we see that the homogeneity of space leads to the conservation of total linear momentum of the system. Now we come to the isotropy of space. That is, if we rotate every particle of the system by the same amount, then if the space is isotropic, then we change Ri to Ri plus delta Ri and delta Ri, where delta Ri is delta phi cross Ri. That means every particle of the system has been rotated by a constant amount thus, and we know that delta Ri dot is equal to delta phi cos Ri dot. This now we come to the Lagrangian. The Lagrangian delta L, the change in Lagrangian is given by del L del Ri dot delta Ri plus del L del Ri dot delta Ri dot. I is equal to 1 to n. Then we know that this is Pi, this is Pi dot, and so we have summation over I is equal to 1 to n. This is Pi dot times delta Ri means delta phi cross Ri. This is Pi dot, I missed the dot. Then for this term, this is Pi dot delta phi Ri dot. Now we change this. First interchange between phi and p, and then p and r. So the resulting thing is that delta phi dot Ri cross Pi dot plus delta phi dot Ri dot cross Pi. The phi can be taken out, so delta phi can be taken out. The resulting quantity is I is equal to 1 to n, and we have, this is Ri cross Pi dot plus Ri dot cross Pi. So this can be written as delta phi dot ddt of Ri cross Pi. So this is the angular momentum of the ith particle, and this can be written as delta phi dot summation over I is equal to 1 to n dli dt, where li is equal to Ri cross Pi, are the angular momentum of the ith particle with respect to origin, and this can be written as delta phi dot ddt of L, where L is the vector sum of individual orbital angular momentum. Since delta phi is arbitrary, we may rotate each of the particle by any angle. Since delta phi is arbitrary, we see that the isotropy of space leads to the fact that del L del T is equal to 0, del L del T is equal to 0, which says that L is equal to summation over Ri cross Pi is a constant vector. So this is the conservation principle of angular momentum. So in this case we have applied the Noita Theorem or established Noita Theorem for three specific cases. The homogeneity of time leads to the conservation of total mechanical energy. The homogeneity of space leads to the conservation of total linear momentum of the system, and the isotropy of space leads to the conservation of total angular momentum of the system.